Good morning students. Today is lecture 3 under module 10 and today we will be discussing about methanol production and utilization. So, let us begin. Methanol as an alternative biofuel for internal combustion and other engines has gained interest since last few years. Methanol is being used as fuel either in combination with gasoline or independently. Methanol or methyl alcohol is an organic compound CH3OH with a molecular weight up to 32.042. Nowadays, it is one of the main competitors to hydrogen as a clean fuel. The use of hydrogen appears to be most promising from an energy point of view. In fact, it has the highest energy content per unit weight of any known fuel 142 kilojoules per gram. It is a very big energy content you can say, and in comparison to the other natural gases it is environmentally safe. At present, the problems related to the use of hydrogen as a new energy resource are the cost of purification process and the difficulties linked to the infrastructure for storage and transport. You must be aware that huge work across the entire world is going on for hydrogen storage, right. See, still many things are unanswered and people are working day and night to make it successful. There are interesting works already being commercialized also. And now, the most important competitor appears to be methanol, which has an octane number of 113 and a density that is about half that of gasoline. Among several uses, methanol can be mixed with conventional gasoline without requiring any technical modification in the vehicle fleet. So, that is the most interesting part of methanol blending. So, most of the methanol fuel vehicles are use M85. So, M85 is nothing but a mixture of 85% methanol and 15% of unleaded gasoline. Furthermore, methanol can be used as a convenient energy carrier for hydrogen storage and transportation, as an easily transportable fuel, and also in the chemical industry as a solvent and as a C1 building block for producing intermediates in synthetic hydrocarbons, including that of polymers and single cell proteins. Methanol is a extremely valuable solvent for most of the chemical industries. For all these reasons, methanol is considered to be the transition molecule from fossil fuels to renewable energies. It is only slightly soluble in fat and oil and represents one of the most important chemical raw materials. Indeed, the primary use of methanol is in the chemical industry as either a feedstock solvent or a co-solvent. Methanol is less expensive to produce in comparison to ethanol as a fuel, when we will talk about ethanol use as a fuel. However, it has a lower energy density and it is little more toxic than that of ethanol. Now, methanol may be made from hydrocarbons or renewable sources, in particular natural gas and biomass respectively. That is why we are discussing it under this course. It can also be synthesized from carbon dioxide and hydrogen. For direct engine application, usually a blend of methanol, ethanol and petroleum is any time preferred than individual fuels. Okay. So, if you talk about the methanol produced and it is being used, approximately 65% of methanol produced worldwide is consumed for the production of acetic acid, vinyl and methyl acetates, methyl methacrylate, methylamines, MTB, that is methyl tert-butyl ether, fuel additives and other chemicals. The remaining portion is converted into formaldehyde and the resulting products as shown in the following figure. You can see the, if you go by percentage, formaldehyde is the highest. Okay. So, methanol was first produced by destructive distillation or we can call it as pyrolysis of wood, and was known as wood alcohol by the British scientists. During the OPEC 1973 oil crisis, methanol was produced from coal as a proven fuel with a well established manufacturing technology and sufficient resources to replace gasoline. Later on in 1986, Swedish Motor Fuel Technology Corporation extensively reviewed the use of alcohols and alcohol blends as motor fuels. So, they reported in detail the methanol production from natural gas, very heavy oils, bituminous salts, coals, peat as well as biomass. Slowly then methanol's use as a fuel started gaining interest, basically as a blend. In 2018, Government of India announced that if feasible, passenger vehicles will run on 15% methanol mixed fuel. At present, vehicles in India use up to 10% of ethanol blended fuel. If approved by the government, it is estimated to cut monthly cost at least by 10%. Now, we will discuss about the various ways to produce methanol. So, the first one is methanol from natural gas. Many technologies have been developed over the years to produce methanol from different sources. In fact, it can be synthesized from several carbon containing feedstocks including natural gases. It could even be produced right at the gas well by oxidative transformation, that means production at source, which looks good from the economical point of view. Then coal, biomass or carbon dioxide, the latter directly recovered from the atmosphere. Currently about 90% of methanol is produced from natural gas. The process route for the production of the simplest alcohol is relatively straightforward, involving the three following basic steps. The first one is the production of syngas or synthetic gas. Second is the conversion of syngas into the crude methanol. Third and one of the most important aspect is of course distillation of the crude methanol to achieve the desired purity. The process of converting syngas into crude methanol occurs at a pressure of 50 to 100 bar and a temperature of 200 to 300 degree centigrade. The main reactions involved into methanol synthesis are shown below. The first one is hydrogenation of carbon monoxide. So, carbon monoxide plus 2 hydrogen gives us methanol, then it is divided into 2 consecutive steps. So, carbon monoxide plus hydrogen gives us formaldehyde, formaldehyde plus hydrogen gives us methanol. Again the last one hydrogenation of carbon dioxide. So, carbon dioxide plus 3 hydrogen gives us methanol plus water. So, you can see you have to understand that these all reactions are happening simultaneously. Okay. So, in addition the conversion of synthesis gas is subjected to a thermodynamic equilibrium that limits the process to a lower conversion per pass, therefore, implies a large recycle of the unconverted gas. The resulting cycle, recycle and cooling duty are largely responsible for the investment cost of the process segment. Over the years, several solid catalysts have been developed in order to maximize methanol yield and selectivity and minimize byproduct formation. So, this is a conventional methanol production schematic representation. So, we will try to understand in a nutshell the flow diagram, the block diagram basically. So, steam plus natural gas, okay. They are fed to a reformer, the first reformer which something looks like this in a industrial scale. Okay. So, you get a fuel gas here and you can also partly supply the natural gas or fuel. Then what you get is basically the synthesis gas, carbon monoxide hydrogen or carbon dioxide plus hydrogen. These are the two reactions that will happen inside the methanol converter. Now, from the methanol converter we will get the hydrogen parts. So, we can again purify this hydrogen and it can goes to burners or to the hydrogen consumers, okay, depending upon what is the purity. And this is how it looks like a methanol converter in the real life industrial parlance. Then the methanol water mixture, okay, it goes to a distillation unit, something it looks something like this. Okay. So, where it is purified to get a almost pure 99% pure methanol, and the leftover water can further be recycled to various process streams. Next is the BASF. It is a German company developed process, it is a high pressure method. Now, a great variety of oxides and metals have been tested as hydrogenation catalysts, excluding only the 8th group of the periodic system, almost all have been used. So, all reactions were carried out at high pressure 250 to 300 bar and a high temperature 320 to 450 degree centigrade. So, among all, two catalysts which is given a very extremely high selectivity and the best results in these reaction conditions were zinc oxide Cr2O3 and zinc oxide copper oxide catalyst. So, bimetallic catalyst basically, right. So, on this basis many studies have been done to investigate the reaction mechanisms of methanol production in presence of the above mentioned solid catalyst. These are solid catalysts because these heterogeneous catalysts are easy to recover from the liquid phase stream, okay, and you can regenerate and reuse it. Homogeneous catalyst we cannot do it, okay. So, as shown below, two different ways are proposed, both involving the adsorption of carbon monoxide and hydrogen on the surface of the catalyst. So, this is the mechanism A and the second one is shown in the next slide. So, in the mechanism A shows that the reaction takes place in 4 consecutive hydrogenation steps. So, that there are 4 consecutive hydrogenation steps, you understand that this is the surface of the catalyst, right. Carbon monoxide, okay. Then hydrogen is getting this one attached on the surface or adsorbed on the surface of the catalyst. So, in 4 subsequent steps, so you get here methanol, okay. Then in the second one, this is mechanism B. Here in the mechanism B, both carbon monoxide and a hydroxyl group on the catalyst surface are involved. So, in the mechanism A, only carbon monoxide and hydrogen were involved. Here one carboxylic group, you can see that C double bond O, this carboxylic group is coming into picture and it is getting adsorbed on the surface of the catalyst, and then we have the reaction proceeds in this way. Okay. So, in the first step, it takes place by insertion of a carbon monoxide to formate intermediate. Okay. So, the formate intermediate is this COOH. Okay. Subsequent hydrogenation and dehydration leads to the formation of methanol passing through an methoxide intermediate. Okay. Now, it is noteworthy that these two mechanisms proposed differ not only for the intermediates formed, but also for the way in which they are bonded to the catalyst surface, that is with a carbon atom in the mechanism A and with oxygen in mechanism B. So, that is the basic difference between these two mechanisms. As a result, catalytic cycles of the zinc oxide Cr2O3 and zinc oxide copper oxide catalyst were proposed, and they have been found to be extremely selective. So, the next is the Imperial Chemical Industries process, which is a low pressure method. Now, in the 1960s, the BASF high pressure method was overcome by a low pressure method created by the ICE. Now, it is ICI, now it is Johnson Matthey. So, they developed a new route for methanol synthesis in a pressure range equal to 35 to 54 bar, much lower than that of the BASF method, and a temperature ranging from 200 to 300 degree centigrade, again a lower temperature range than that of the BASF. Now, this was made possible not only by the discovery of a new more active and selective copper based catalyst, so copper, zinc oxide, alumina Al2O3, but also by the development of a new advanced purification process for synthesis gases, which allowed them to use sulfur chlorine free syngas. Now, I have told you many times that any such processes, when we talk about the biomass conversion into value added products, purification step after the product is formed, okay, either that is in the gaseous phase or in the liquid phase, maybe sometimes in solid phase also, the purification phase is the most time consuming, energy consuming, as well as it is a costly affair. Almost 40% of the product cost goes to the purification. So, if you have a excellent purification process which is economical, then the product price will come down, and as well as you will get a higher purity product. That is what it has happened in the ICI method. Despite the fact that the catalytic power of copper zinc catalyst in methanol synthesis was already well known, this was not exploited commercially due to their low lifetime and the low thermal stability, mostly caused by their deactivation by poisoning. So, very quickly they get deactivated. So, that is once they deactivate, you call them catalyst poisoning. So, they are no more taking part in the reaction. Now, these problems were overcome thanks to the addition of alumina, which increases the stability of the copper zinc oxide catalyst and inhibits the thermal formation of the copper crystallites. So, the next and most important process is of course methanol from coal and biomass. The use of biomass and char represent another route for methanol production. Nowadays, new industrial research is trying to solve the triple problem of energy demand, waste management and greenhouse gas emissions. Waste to energy technologies convert solid waste into various forms that can be used to supply energy, which can be derived by the thermochemical processes. The latter is a better route than biochemical conversion due to a higher amount of feedstock transfer and a faster conversion rate. The production process for obtaining methanol from coal and biomass is similar to that for the production of methanol from natural gas, subdivided into the following three steps: syngas production, synthesis of the crude methanol and purification. In the first step, coal or biomass is converted inside a gasifier into the gaseous products, which consist of biogas, that is methane and carbon dioxide, syngas hydrogen, carbon dioxide and carbon monoxide, pure hydrogen and maybe some alkaline gases. Now, the gasification process is a thermochemical conversion technique, which we have discussed in detail in our previous classes, that allows the conversion of solid biomasses into gaseous mixtures with the help of gasifying agent. It can be air or oxygen, steam and flue gases. Now, this process using high temperatures in the presence of oxygen aims for a large scale development to overcome the current limits, that is the low hydrogen production and high tar content in the syngas. In fact, the unwanted tar may cause the formation of tar aerosols and polymerization into more complicated structures, which are not favorable for hydrogen production through steam reforming. For this reason, several research groups have focused their studies on maximizing the hydrogen quantity produced and minimizing that of tar. Under typical gasification conditions, oxygen levels are restricted to less than 30% of that required for complete combustion, and carbon monoxide and hydrogen are the major products. Methanol is produced from syngas utilizing conventional gasification of biomass at high temperatures, almost at 800 to 1000 degrees centigrade, and it can be made with any resource containing carbon such as coal or solid waste. Now, we will look for the reactions. The conversion of gaseous products involve many reactions. So, 5 main reactions are being listed here. The Char gasification reaction. So, carbon plus water gives carbon monoxide plus hydrogen, then water shift gas reaction. So, carbon monoxide plus water gives carbon dioxide plus hydrogen, steam reforming of methane, methane plus water gives carbon monoxide plus 3 hydrogen, a Borward reaction. So, carbon plus carbon dioxide reacts to give us 2 moles of carbon monoxide, then methanation reaction. Here the carbon plus 2 hydrogen gives us methane. Now, again the same methane gets converted to carbon monoxide. So, all these are going on simultaneously. However, unconventional gasification processes applied to biomass do not always produce a syngas with the quality that is required for methanol synthesis. So, please note that any syngas that is produced through biomass gasification cannot be used to convert it to be methanol. We need certain purity. So, one of the biggest problem in the gasification of biomass is the formation of tar and char via the reduction of the carbon oxides. Now, the synthesis gas for methanol production should only contain a small proportion of inert gas components. In fact, the use of air as a gasification agent always results in a syngas with a high nitrogen content, which is not actually desirable when you talk about towards methanol conversion. So, for methanol synthesis, the optimal hydrogen carbon dioxide molar ratio in the syngas is greater than 2, and then the gasification of biomass always results in a gas with a too low hydrogen to carbon dioxide ratio. So, this is the problem with biomass to methanol. So, usually the water gas shift process is the most frequently used process for ensuring a suitable ratio of carbon dioxide, carbon monoxide, hydrogen, and may lead to convert the carbon monoxide to carbon dioxide. If carbon monoxide is present when the syngas is combusted in gasification, the carbon dioxide removal efficiency will be limited, since the carbon monoxide in syngas will be converted to carbon dioxide during the combustion process. The reaction temperature for the water gas is 375 degrees centigrade and the pressure is 40 bar. Carbon monoxide is converted to carbon dioxide and hydrogen. The carbon dioxide produced during the water gas shift process must be separated from the syngas in order to ensure a suitable ratio of the carbon dioxide, carbon monoxide, hydrogen. For the commercially available methanol production catalyst, that's required minimum is 5:28:63 in that ratio. Okay. So, sulfur must be removed from the syngas, as sulfur is very hazardous for the catalyst used for methanol production as well as during the water gas shift reaction. So, now we will discuss about the methanol from catalytic hydrogenation of carbon dioxide. Carbon dioxide is a linear molecule that is very stable and needs extra efforts to make it reactive. Owing to its high stability, a substantial energy input, optimized reaction conditions, and a catalyst with high stability and activity are required for converting carbon dioxide into value added chemicals. Converting 1 mole of carbon dioxide to methanol requires an energy input of about 228 kilojoules and 6 electrons to reduce the carbon 4 plus of carbon dioxide to C2 minus of methanol. So, the carbon oxygen bonds are very strong and high energy is required for breaking them. For this reason, in order to convert carbon dioxide into methanol, a very good catalytic system is the utmost need. So, the reaction of this catalytic conversion of carbon dioxide into methanol by hydrogenation is given below. So, carbon dioxide plus 3 moles of hydrogen will give us methanol plus water. The next one is methanol biosynthesis way. The catalytic conversion of methane to methanol is affected by enzymes including methane monooxygenase. So, these enzymes are mixed function oxygenases, that is oxygen is coupled with the production of water and NAD plus. So, this is the reaction methane plus oxygen plus NADPH plus hydrogen gives us methanol plus water plus NAD plus. Both iron and copper dependent enzymes have been characterized. Intense but largely fruitless efforts have been undertaken to emulate this reactivity because of various process optimization things as well as the yield. Now, we will talk about the various uses of methanol. So, the first one and one of the most important is of course, methanol to various platform chemicals such as formaldehyde, acetate or acetic acid and MTBE, methyl tert-butyl ether. So, methanol is primarily converted to formaldehyde, which is widely used in many areas, especially polymers. The conversion entails the oxidation reaction. 2 moles of methanol plus oxygen will gives us 2 moles of this one formaldehyde and water. So, methanol and isobutene are combined to give MTBE, the methyl tert-butyl ether. So, MTBE is a very important class of chemical, okay, and it is a major octane booster that is getting used in gasoline. So, acetic acid can be produced from methanol via following the Cativa process. It is a very well known process and has been well adapted also. The Cativa process is a method for the production of acetic acid by the carbonylation of methanol. The process is similar to the Monsanto process and was developed by the BP Chemicals. It is based on a iridium containing catalyst such as this complex IRCO2 I2 complex. So, it is a iridium based catalyst. So, let us see how it happens. I will explain you in the next 2 slides. You can just have a look at this particular cycle, how it is happening. I will explain this. Okay. So, please look at the first, second, third and fourth, 4 different intermediate steps. So, the base molecule is nothing but methanol, from where we are producing various products. So, this is here the starting material methanol. Okay. We will come back to that inner cycle later on. So, let us start with the one. So, methanol is converted to methyl iodide. Okay. Methanol is getting converted to methyl iodide. How it is? I will explain it in the next slide. So, methyl iodide is the starting reaction, you can say that. So, the reaction of methyl iodide with the square planar active catalyst species 1. So, this is the species 1 with iridium in the center, okay, to form octahedral iridium 3 species in the section 2, you can say here. Again you can see that IR3. Okay. Now, the next is this oxidative addition reaction involves the formal insertion of the iridium center into the carbon iodine bond of the methyl iodide, right. So, after the ligand exchange, that means iodine for carbon monoxide. So, in the next phase what is happening here, iodine is getting replaced with a carbon monoxide. So, you can see that one more carbon monoxide is coming here. Okay. The migratory insertion of carbon monoxide into the iridium based carbon bond in the step 3 to step 4 results in the formation of a square pyramidal species with a bound acetyl ligand. Okay. So, this is a square pyramidal species with a acetyl ligand here C double bond O. Now, the active catalyst species 1 is regenerated by the reductive elimination of acetyl iodide from 4, okay, and via a de-insertion reaction. So, you can see that I minus is getting removed from here and this particular complex is getting converted to the first species, which is the starting reaction species, right. Now, the acetyl iodide is hydrolyzed to produce the acetic acid product, in the process generating a hydroiodic acid, which is in turn used to convert the starting material, that is methanol, to the methyl iodide used in the first step. You can see how it is happening and formally you are getting the your product of interest. This is the inner circle, where this particular pathway is responsible for forming methyl iodide from methanol. Okay. So, this is the process detail. So, the next is methanol to DME, the dimethyl ether. Now, in the last 10 years, one of the most promising technologies is the use of methanol as a C1 building block in the petrochemical industry, and a wide part of its production is consumed in the manufacturing of DME as an alternate fuel. Now, DME has a octane number and ignition temperature close to that of diesel fuel, that is why it is so important. Okay. Now, it leads to lower NOx emission, less smoke, less engine noise than the conventional diesel engine, and furthermore can easily be transported. DME can also be used as a chemical feedstock for manufacturing of many products such as short olefins, for example, ethylene and propylene, gasoline, hydrogen, acetic acid and dimethyl sulfate. So, the current DME manufacturing process is a double step indirect synthesis one, in which methanol synthesis carried out by one of the above mentioned technologies is followed by dehydration. 2 moles of methanol gives us CH3 OCH3 plus water. Okay. Another developing process involves the direct synthesis of DME from syngas. Now, in this process syngas carbon monoxide and hydrogen with a 1:1 molar ratio are converted to DME in the presence of a catalyst. So, 3 moles of carbon monoxide plus 3 moles of hydrogen in the same ratio will give us DME plus carbon dioxide. Now, hydrogen production from methanol. We will discuss a few steps. The first one is of course, a few processes. The first one is methanol decomposition. So, methanol decomposition is an endothermic reaction to produce hydrogen and carbon monoxide from methanol. So, methanol is giving us CO plus 2 H2. You can see the delta H is 90.1 kilojoules per mole. And this is applicable to the recovery of waste heat of around 200 degree centigrade from industries. For the development of a heat recovery system, new catalysts that can be active even at temperatures below 200 degree centigrade are indispensable. Usami et al. In 1998 for example, have tested 15% weight of palladium zirconium oxide, then PdPr2O3 and PdCuO2 catalyst. Now, these catalysts prepared by co-precipitation can produce high catalytic activity in the selective decomposition of methanol to carbon monoxide and hydrogen at a temperature as low as 200 degree centigrade. It is a beautiful work, the reference is given here. Okay. You can read more if you are interested. The next one is methanol water solution electrolysis. Another way to produce hydrogen from methanol is by methanol water solution electrolysis using an electrolytic cell. Now, generally electrolysis of water is the best option for producing very pure hydrogen and that too very quickly. As in the electrolysis of water, in the methanol water system, the hydrogen produced is very pure, almost 95.5 to 97.2 mole percent, but the theoretical voltage of the system is much lower than that of the water electrolysis process, 1.23 volt in water electrolysis compared to 0.03 volt, very less it is, okay, in methanol water solution electrolysis. So, in methanol water solution electrolysis, hydrogen is produced by applying DC voltage to the electrolytic cell. So, in this system the overall reaction can be written as that methanol plus water gives us carbon dioxide plus 3 moles of hydrogen. The reaction at anode and cathodes are like this. So, CH3 methanol plus water is carbon dioxide plus 6 proton plus 6 electron, that is in anode, then 6 proton plus 6 electrons gives us 3 moles of hydrogen at cathode. Now, at the anode methanol reacts with water to produce carbon dioxide. So, exhausted outside the anode basically and protons and electrons. Now, the protons produced by the anode reaction move to the cathode of the electrolytic cell through the proton exchange membrane. Okay, there is a PM membrane in between, and the electrons produced by the anode reaction move to the cathode through the external circuit containing the DC power supply. This is how it happens, right. So, you can imagine it is a schematic representation, simplified one. You can see that this is a anode part, this is a cathode part, and here this is your PEM, okay, proton exchange membrane. It is a membrane, right, solid membrane. Now, you can see that when the anode these reactions are happening, the protons are passing through the this one proton exchange membrane, PEM membrane, okay, to the cathode side, where it is combined with the electrons and resulting in hydrogen. Okay. So, at the cathode, protons supplied from the anode react with electrons supplied from the anode. Hydrogen production by methanol water solution electrolysis is suitable for only potable power applications, because methanol water solution electrolysis can start up and shut down in a moment and can produce hydrogen at a lower temperature, very fast, quick. Okay. But for the smaller applications, the voltage needed in methanol water is 3 times lower than that of the water solution electrolysis. So, next one is methanol steam reforming. The production process that is much used in the production of hydrogen is the methanol steam reforming, popularly called as known as the MSR pathway. Okay. Now, compared to the other fuels, methanol presents several advantages of hydrogen production. In fact, the absence of a strong carbon-carbon bond facilitates the reforming at low temperatures, a range of temperature that is very low when compared to other common fuels. The overall reaction for the MSR to the production of hydrogen is expressed as methanol plus water is carbon dioxide plus 3 moles of hydrogen. The delta H is little lower here compared to other reaction, 49.7 kilojoules per mole. Then is next is partial oxidation or ATR, autothermal reforming. So, unlike MD and MSR, partial oxidation of methanol is an exothermic reaction. So, no additional heat is needed. However, the temperature control can become difficult. The addition of steam into POM leads to the ATR of methanol. Now, the addition of steam in ATR intensifies hydrogen production, but it lowers the reaction temperature and thereby the reaction rate. In contrast to MSR and methanol ATR, relatively less hydrogen is produced from POM. Now, POM can be expressed as methanol plus half oxygen is 2 moles of hydrogen plus carbon dioxide with a delta H is 192.3 kilojoules per mole and say higher delta H you can see if you compare to other reactions. Now, by virtue of more heat released from POM being employed for chemical reactions, POM is kinetically faster than the MSR and methanol ATR, implying that a smaller reactor is achievable or it will be good for carrying out the POM. Now, we will discuss about the methanol fuel cells. Okay. So, one type of proton exchange membrane fuel cell is that DMFC, which is direct methanol fuel cell. Now, that uses methanol or methanol solutions as a fuel and works at an ambient temperature. Now, this is the reaction. So, methanol plus 1.5 oxygen gives us carbon dioxide plus 2 water. The structure of the DMFC consists of 2 porous electrolytic electrodes on both sides of a solid polymer electrolyte membrane. The thermodynamic reversible potential for the overall cell reaction is 1.214 volt. Methanol and water are oxidized in the anode catalyst layer known as ACl and release electrons and protons according to this reaction. So, methanol plus water gives us carbon dioxide plus 6 proton plus 6 electron. You can see how it happens into subsequent representation. Okay. This is the overall representation where you can see that this is the chamber. Here you can see that methanol is getting fed to the chamber, okay, and this part is anode, this is cathode, the electron is getting flown from like this way from anode to cathode. Okay. Then you have to supply oxygen, so it will result in carbon dioxide this side, water that side, and this is a more elaborate way of representation. Now, these electrons are transported through an external circuit to the cathode, while the protons penetrate the electrolyte membrane to the cathode. Right. So, in the cathode catalyst layer, that CCl layer, the oxygen from the ambient atmosphere reacts with electrons and protons and generates water. So, 6 protons plus 6 electrons plus 1.5 moles of oxygen will gives us 3 moles of water. Okay. So, you can see here this is the both are same, here the it is written in a better expressive way. So, you can see that methanol, okay, is getting converted to carbon dioxide, the electron is getting circulated via the load, right, to the from anode to cathode. This is how it flows, it is very nicely represented there, and the hydrogen it is getting transported via this membrane, the solid electrolyte membrane, okay, and getting to the other side where oxygen is getting converted with the help of a proton that is coming from this side to that side and with the help of electrons to water. Okay. This very simplified system, okay, and it has lot of applications. Now, DMFC was initially developed in the United States by several organizations including NASA during the 1990s. So, it operates at a temperature range of 60 to 130 degree centigrade. Current DMFCs are limited in the power they can produce, basically they produce small amount of power, but it can still store a high energy content in a small space. That is the beauty of DMFCs. This means that they can produce a small amount of power over a long period of time, sustainability. Okay. Now, this makes them ill suited for powering large vehicles, but they are very ideal for smaller vehicles such as forklifts and tuggers. Now, DMFCs are thus used where the power requirement is modest, such as mobile electronic devices or chargers and portable power packs. Military applications of DMFCs are an emerging application since they have low noise and thermal signatures and they have absolutely no toxic effluent. So, with this I wind up today's lecture. So, if you have any query, please register it in the SWAYAM portal, or you can always free to drop a mail to me at kmohanty@iitg.ac.in. The next module, that is module 11, is dedicated to the organic commodity chemicals from biomass. Okay. So, various types of platform chemicals that are being produced from biomass, we will learn about that, so thank you very much.